In this video, I'll talk about neutral voltage. So when you have a Y and the neutral is not grounded, and especially if you have unbalanced, like unbalanced load, for instance, what happens to the voltage from the neutral to ground? So, and I'll demonstrate this through an example to make, that way it makes more sense. So let's assume we have unbalanced 3-wire Y connected load. For instance, and you can think of it, the neutral probably existed, but somehow it became, like it got disconnected for whatever reason. So either the neutral was there and it somehow became disconnected, or the neutral actually was not there. So for now, let's assume the source is grounded as a reference. So if the neutral, so like since this neutral here, the source neutral is grounded, so it's at zero potential. Now, if the neutral was grounded, you know, and assuming this impedance, the impedance of the neutral, if I call that Zn, for instance, if we assume that's zero, so the load neutral will be at the same potential as the source neutral, so it would be 0 volts. Obviously, if this is not zero, so there will be some voltage drop. But now, if the neutrals are not tied, or the neutral is not connected to ground, so this neutral now will not be at zero. It's going to shift from zero basically. So because it's not tied to ground. And that's only if there's unbalance due to, say, like in this case, as we'll see, the load is unbalanced. So that neutral voltage will not be zero. It will shift from zero. So we have the source voltage is 480 volts with an angle of 0 degrees. BC, and these are complex or phasor quantities. So VBC is 480 with an angle of negative 120 degrees. VCA 480 with an angle of 120. So basically we're assuming, if you draw the phasors with VAB as a reference, we're assuming counterclockwise as our positive kind of direction. So then, since they are balanced in this case, VBC would be here, because you're going the opposite direction. So this is negative 120 degrees, and VCA would be here, because this is, if you go from here to here, it's a positive or plus 120 degrees. So then we have the load ZA. So the line, so this here is, so the source is connected to the load through a line, So the lines have equal impedances. For simplicity, it's just 1 ohms. Then these are the loads, lowercase a, b, c, and as you can see, they're unbalanced. They have different magnitudes and different angles. So our task is to calculate the line currents, the currents flowing through the lines. Then we want to calculate the neutral displacement or shift, neutral shift. So basically this neutral here, we want to calculate this voltage, if I call that Vn. So if the load was balanced, if everything was balanced, then if you draw, if you draw the triangle, those are the line-to-line voltages. Then in the middle would be kind of virtual or the neutral. So you would have A, for instance, B, C. So this would be the connection point or the neutral. So you can see it's kind of at the center. So because everything is balanced, and the line-to-line voltages AB, BC, CA will always be balanced regardless. But the line to neutral or line to ground from voltages will not be balanced. So what happens is now, so what I drew here is under balanced conditions. Now let's assume, or I guess in our case, the load is not balanced. So now this end will shift. It's not going to stay at the center of the triangle. It might shift, it depends on the on the unbalance and everything. So, but it's going to shift. That's what we mean by shift or displacement. So the neutral, it might shift to this point here, for instance. If I can get my pen. So it might shift to this point here. So just so we don't cause any confusion, let's call that O. Now the neutral moved from N when it was under balance conditions, to the point O. So that's what happens basically. So the neutral will shift. Now your voltages will shift as well. So now you're going to go from A to O and from C to O and B to O. And as you can see, they are no longer equal, So that's what we mean by neutral shift. So basically, under balanced conditions, if you draw the kind of the triangle, your neutral will be at the center of the triangle. However, if there's unbalanced conditions, the neutral will no longer be at the center point or at the center of the triangle. So it's going to shift somewhere else, which causes the phase voltages, or ground line to ground voltages, or line to neutral voltages, from A to that new neutral point and B to that neutral point, C to the neutral point, they are no longer equal. So that's really what we mean by the neutral. When you hear someone saying the neutral shifts or it's displaced due to unbalanced conditions. And unbalanced conditions, they can be caused by unbalanced load, unbalanced line impedances, line to ground faults, anytime you have unbalanced, basically, conditions. So now, with that in mind, so how do we calculate that neutral shift? So just to avoid any confusion, so lowercase n, that's like the neutral point, which is at the center of the triangle under normal conditions. But under unbalanced conditions, we're gonna call it O. But anyway, so now in this video, I will calculate the neutral shift using mesh currents. So, I took the circuits basically, and I just kind of showed, here's one mesh current, I1, here's I2. So then basically, I just wrote mesh currents, basically VAB. So if I start from here, so A is, B is here. So if I just go from A, so it's IA, or sorry, I1 times ZA, because it flows through Z uppercase A and Z lowercase a. So that's what you see here. Then I come this way, so then the current going this direction is I1 minus I2, so that's times ZB plus ZB, lowercase and uppercase b. So then just kind of rearranging to kind of factorize I1 and I2. So just kind of doing some algebra here. So this term here, kind of the same here. Then I1 times ZB plus ZB. So I brought that. So that's what you see here. Minus I2 times ZB plus ZB is here. So just algebra basically. So I can factor I1 on one side and I2 on the other side. And what, as you will see, I'll put in a matrix format. So then what I come up with is I1 times quantity uppercase, or ZA plus ZA plus ZB plus ZB minus I2 times ZB plus ZB, which is just equal to VAB. So that's, so equation 1. Then I can go around I2 mesh and do the same thing. So VB is here, VC here. So I'm going to go from B, basically I'm going to go this way and come around. So if I do that, VBC is equal to, because the current flowing in this direction here is I2 minus I1. So that's what you see here, times ZB plus ZB. Probably I should have put different symbols just to avoid confusion. But, so one ZB is lowercase, B1 is uppercase. Plus I2 times, ZC plus ZC. So again, just doing some algebra because I want to put I1 on one side and I2 on the other side. So I get this equation. So I have two unknowns and two equations. I should be able to solve for I1 and I2. So again, so here's equation 1, here's equation 2. So then I just plug the numbers here. ZA, uppercase A, is just 1 with an angle of 0. So I just plug the numbers basically. And if I simplify, I get this quantity here. So I1 times 7.8861 with an angle of 7.48 degrees plus I2 times 4 with an angle of 180 degrees equals 480 with an angle of 0 degrees. So that is equation 1 with our values basically. So if I do the same thing for equation 2, I carry out the calculation. I get I1 times 4 with an angle of 180 degrees plus I2 times 8.7 with an angle of 13.29 degrees equals 480 with an angle of negative 120 degrees. So that is my second equation. And I color coded them. I1 is in blue, I2 is in green. So I just kind of showed the two equations here with values for simplicity. Now I can put them in matrix format. So I1, I2 here, and voltage is just here. Then the terms that I multiply I1, I2 are basically here. So if you use calculator or MATLAB or some kind of program and you plug the numbers in, hopefully if there is a computation error, please let me know in the chat and I'll make sure I put a note in the comments. But I checked, so hopefully I didn't make any mistake. So anyway, it comes out to I1 is equal to 58.9961 amps with an angle of negative 39.56 degrees. Then I2 is 65.4 with an angle of negative 109.15 degrees. So those are my final values. Now, what I'm really after is the line currents, I, A, B, C, all uppercase. So if I go back here, I1 is just equal to IA, which is here. So that's easy. Then IC is kind of flowing opposite to I2. So it's that's why I added a negative sign here. So it's negative I2. So you get this value here. Then IB is I2 minus I1 because IB is flowing this direction, I2 is flowing in its direction, I1 in its opposite direction. So if you take the difference, so then you just plug the numbers and you get this value here. So as you can see, due to the unbalance, the line and phase currents, in this case, since the load is connected in a Y, the phase currents and line currents are the same. So because of the unbalanced situation, the currents are not balanced, and it's very clear from here. You can see IA is 58.9961, IB is 71.18, and IC is 65.4. And even the angles are not balanced, because if they were balanced, they would be displaced by 120 degrees, but they are not. So that's one thing the unbalance causes, so the currents are not balanced. Now we want to calculate the neutral shift. So like I was saying earlier, and I just kind of showed, so these are the given values. This is what I calculated just for simplicity or for convenience. So let's call N the neutral point under balance conditions, and that's what I'm showing here. But just to differentiate it from when the neutral shifts, as I showed earlier, so when you draw the triangle, if under balance conditions the neutral point is here, under unbalanced it might shift somewhere else. So let's call that O instead. Just kind of, we know when you hear O, it means it's the shifted neutral point. So now we want to calculate the voltage from lowercase a to O, to the neutral, to the shifted neutral point, basically. So VAO is equal to, it's just Ohm's law, basically. So it's just current flowing through load impedance, ZA with lowercase a is just IA uppercase A times ZA lowercase a. I know both quantities, so if I plug in the numbers, I get 176.988 with an angle of negative 19.56 degrees, and that is voltage in volts. So if I do the same thing for BO, so here's the equation. I plug in the numbers, I get 213 volts with an angle of negative 160.12 degrees. So VCO, kind of the same thing. I get 261.6 with an angle of 100.85 degrees. So clearly the neutral shift, or the unbalance, actually, the unbalance caused the line to neutral voltages to shift across the load impedances. So you can see it here. For A phase, we got 176. B phase, it's 213, and C phase is 261. So it's clearly the unbalance caused the neutral to the line to neutral voltages to shift. Now we calculated the line to neutral voltages of the load. Now we want to calculate by how much the neutral shifted. Because So VAN, like from voltage from A to the neutral, is really VAO plus VON. So that's kind of what I'm writing here. But anyway, so from O to the neutral, so it's just VOA. So basically, so I'm doing KVL from here. So VON is VOA plus V lowercase a uppercase A plus VAN uppercase N. So that's what I'm doing here. So basically just KVL. So VOA is the same as negative VAO, and V lowercase a uppercase A is the same as negative V uppercase A lowercase a. In other words, what I'm doing here, VOA is equal to negative VAO because I swapped these guys here. And the same thing for VAA. So that's what I'm doing in this equation here. And I know VAA, this guy here, is just Ohm's law. So I know VAO from here. I know the current through phase A or IA. I know ZA. So I can calculate that. And I know VAN, which is just the source voltage, which is basically VAN will be 480 volts divided by root 3. But the line to neutral will be lagging the line-to-line voltage by 30 degrees. So that's why I include a negative sign. Because we're assuming positive sequence and counterclockwise rotation. So that's why you see, so 480 divided by root 3 is 277. And since the line to neutral is lagging the line to line by 30 degrees, that's why I show the negative 30 here. So if you carry out the calculation, you get 50.0002 with an angle of negative 56.45 degrees, and that's in volts. So clearly the neutral voltage is not zero, so it's shifted from zero. And that's important to remember, that there will be voltage from the neutral, it's not going to be zero. So anytime you have unbalance. So in the next video, instead of calculating this neutral shift with mesh currents, we'll use KCL, and it will be a lot simpler. So thank you and have a great day.